After studying this module, you shall be able to number 1. Know about some common discrete probability distributions. Number 2. Know about the possible relations of binomial, Poisson, geometric and hypergeometric distributions. Understand the implementation of probability calculations using probability mass functions, that is PMFs, and derive the general form of a PMF with its mean and variance. In this module, we will study various special probability distributions and its important features on discrete variables. Probability distribution can be used to solve many common business problems. Probability distributions are very significant because they display the probability that a random variable will take on any one of the values within its range. Whenever possible, probability distribution are expressed by means of equations, and tables are given which exhibit the correspondence between the values of random variable and associated probabilities. Also, graph of probability, histograms and bar charts are used to visualize probability distribution. Let us begin by understanding the meaning of uniform distribution. The discrete random variable x is about to follow a uniform distribution when all its outcomes are equally likely, that is, the probability of success of each outcome is constant and equal. The probability distribution for a uniform variable is p of x is equal to 1 upon x, where x is the number of outcomes. Example of uniform distribution is in the case of tossing a single coin. Let the random variable x be number of heads. Then, in this case, the random variable x follows the uniform distribution since the number of outcomes is always 2 with x equal to 0 and x equal to 1. Also, p of x equal to 0 is equal to p of x equal to 1 is equal to half. In a bag of 5 different colored marbles, let x be the color of a marble. Then, in this case, the random variable x follows the uniform distribution since the probability of each outcome is constant with p equal to 1 by 5. Let us consider another example. Rolling a single die, let the random variable x be the score of the dice. Find the probability that the die will land on a number that is smaller than 5. Also, find the expected value of the distribution. This is a case of uniform distribution where each possible outcome is equally likely to occur. Then we have a uniform distribution where p of x is equal to small x is equal to 1 by 6 for x varying from 1 to 3 up to 6. This problem involves a cumulative probability. The probability that the die will land on a number smaller than 5 is equal to the probability of x less than 5, which is equal to p of x equal to 1 plus p of x equal to 2 plus p of x equal to 3 plus p of x equal to 4, which is equal to 1 by 6 plus 1 by 6 plus 1 by 6 plus 1 by 6, which is equal to 2 by 3. Also, the expected value Ex is equal to sigma x px is equal to 1 by 6 into 1 plus 1 by 6 into 2 plus 1 by 6 into 3 plus 1 by 6 into 4 plus 1 by 6 into 5 and plus 1 by 6 into 6, which is equal to 1 by 6 multiplied by 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is further equal to 21 by 6. Moving on to the binomial distribution. Binomial distribution provides an appropriate probability model when sampling is done with replacement from a finite population or when samples are drawn from an infinite population with or without replacement. If P is the probability of success of one trial and Q is equal to 1 minus P is the probability of failure, then the probability of successes in n independent trials is given by B of x, n, p equal to P of x is equal to x, which is equal to f of x is equal to NCx p to the power x q to the power n minus x. This is called binomial distribution. Let us now look at some of the theoretical examples of binomial distribution. A binomial distribution may be used in determining whether a new drug being tested has or has not contributed yes or no labels to alleviating symptoms of a disease. An example might be a free kick in soccer. Either the player scores a goal or she doesn't. Another example would be a flipped coin. It's either a head or a tail. A multiple choice test where you are totally guessing would be another example. Each answer is either right or wrong. Let us look at the condition under which binomial theorem is used. There are 4 such conditions. Number 1. The number of trials n is finite. Each trial is independent of any other trial. There are only 2 possible outcomes of an experiment, that is, a success or a failure. The probability of success P remains constant from one trial to the next, as does the probability of a failure Q. The binomial distribution is biparametric and the parameters are n and p. The mean and the variance of binomial distribution. Mu is equal to np. Variance x is equal to npq. Further, we shall discuss about Bernoulli random variable. A Bernoulli random variable is an example of a discrete random variable, and its distribution is a special case of binomial distribution. A Bernoulli random variable can take only 2 values, one with probability q and 0 with probability 1 minus q, where 0 is less than equal to q is less than equal to 1. Its probability mass function is Px of x is equal to q if x is equal to 1, equal to 1 minus q if x equal to 0, and is equal to 0 otherwise. Let us understand it with the help of an example. Consider the case of a biased coin having the probability of occurrence of a head is 0.2 and that of a tail is 0.8. Consider the case of tossing of such a coin 5 times. What is the probability of getting 3 heads? Also, find the variance and the standard deviation. This is the case of binomial distribution. Here, b, x, n, p, that is binomial formula, can be used. Here, probability of success, that is occurrence of head, is 0.2, that is p is equal to 0.2, x is equal to 3, and n is equal to 5. Now, b of 3, 5, 0.2 is equal to 5 factorial upon 3 factorial multiplied by 2 factorial whole into 0.2 to the power 3 into 0.8 to the power 2, which is equal to 0.1024. Ex is equal to np, which is equal to 5 multiplied by 2 equal to 10. Now, Vx is equal to npq, which is equal to 5 into 0.2 into 0.8, which is equal to 0.8. Next, we have cumulative binomial distribution. Cumulative binomial distribution is more helpful when we are interested in a range of values rather than a single specific number. Cumulative binomial distribution is in the form of capital B of x, n, p is equal to sigma k varying from 0 to x of b k, n, p for x is equal to 0, 1, 2 up to n. Note, however, the values of b, x, n, p can be obtained by subtracting adjacent entries of the two cumulative probabilities capital B x, n, p and capital B of x minus 1 n, p. Since they differ by the single form b x, n, p, that is b x, n, p is equal to capital B x, n, p minus capital B of x minus 1 n, p. We tabulate to cumulative probabilities rather than the values of B of x, n, p because the values of capital B x, n, p are the ones needed more often in statistical application. Moving on to evaluating cumulative probability. Let us understand with the help of an example. Given total number of workers in a mill are 7. Find the probability that at least 5 turned out given the probability of success is 0.4. Given n is equal to 7, p is equal to 0.4, we have to find the probability of x greater than equal to 5, which is equal to b 5, 7, 0.4 plus b of 6, 7, 0.4 plus b of 7, 7, 0.4, which is equal to 1 minus capital B of 4, 7, 0.4, which is equal to 1 minus 0.9037. This is equal to 0.0963. Looking at another example, if the probability is 0.2, then one student will fail. What is the probability that 5 of 18 randomly selected students will fail? Using the relationship between binomial probability to cumulative probabilities, we get B of 5, 18, 0.2 is equal to B of 5, 18, 0.2 minus B of 4, 18, 0.2, which is equal to 0.8671 minus 0.7164. These values are given by the table, which is further equal to 0.1507. Further, we shall discuss the Poisson distribution. The Poisson distribution measures the probability, that is the relative frequency, of a random event over some interval of time or space given the random variable is discrete. It serves as a model for counts, that is x, which do not have a natural upper bound. The Poisson distribution with mean has the probabilities given by f of x, lambda is equal to lambda to the power x multiplied by e to the power minus lambda upon x factorial for x varying from 1, 2, 3 and so on. Moving on to theoretical examples of Poisson distribution. An example of such a situation would be if you know the mean expected number of cancer cells present per sample and wanted to determine the probability of finding 1.5 times that amount of cells in any given example, you would use a Poisson distribution. Number of typing errors on a page. Failure of a machine in 1 month. Two assumptions are necessary for the application of the Poisson distribution. The probability of occurrence of the event is constant for any two intervals of time or space. The occurrence of the event in any interval is independent of the occurrence of any other interval. In Poisson distribution, mean is equal to variance is equal to lambda. Also, the Poisson distribution is uniparametric and its only parameter is the mean lambda. Let us understand it with the help of an example. A manufacturer of television sets knows that average 5% of their product is defective. They sell television sets in consignment of 100 and guarantees that not more than 2 sets will be defective. What is the probability that the TV set will fail to meet the guaranteed quality? Given e to the power minus zero point .5 is equal to 0.0067. Success is equal to the TV is defective. X is equal to number of successes. P is equal to probability of success, which is equal to 5%, which is equal to 0.05. N is equal to 100. Lambda equal to NP is equal to 100 into 0.05 is equal to 5. Poisson distribution is probability of x equal to small x is equal to lambda to the power x into e to the power minus lambda upon x factorial. Therefore, probability of x greater than 2 is equal to 1 minus probability of 0 plus probability of 1 plus probability of 2. This is equal to 1 minus e to the power 0.5 multiplied by 1 plus 5 plus 25 upon 2, which is further equal to 1 minus e to the power 0.5 into 37 by 2. This is equal to 1 minus 0.0067 multiplied by 37 by 2. This is equal to 1 minus 0.12395, which is finally equal to 0.87605. The Poisson distribution is the limiting case of a binomial distribution when the number of trials is very large, that is, when n tends to infinity, and the probability of success is very small, that is, p tends to 0. So that the mean of binomial distribution np is equal to lambda is equal to mean of Poisson distribution, which is finite. Also, variance is equal to np into q, which is equal to np into 1 minus p, which is further equal to lambda into 1 minus p, which approaches lambda as p tends to 0. Understanding with the help of an example. Let x denote the number of plants farmed in a particular area. X is having a Poisson distribution with lambda equal to 3. What is the probability of plantation of at most 4 trees? Also find the variance. This is the case of Poisson distribution. Here, probability of x less than equal to 4 can be computed using the cumulative Poisson distribution table, which gives p of x less than equal to 4 is equal to 0.815. We shall now understand geometric distribution. When in a sequence of n trials which is not fixed, we are interested in the number of trials on which the first success occurs, and if that first success occurs on the xth trial, it has to be preceded by x minus 1 failures, then the probability of getting first success on the xth trial is given by geometric distribution. Given p is the probability of success, 1 minus p is the probability of x minus 1 failures in x trials. X is the number of trials until the first success is observed. Also, the geometric distribution has only one parameter, which is equal to p. Geometric distribution has following 4 properties. First, the experiment consists of a sequence of independent trials. Second, each trial results in one of 2 outcomes, success S or failure F. Third, the geometric random variable x is defined as the number of trials until the first S is observed. And fourth, the probability Px is the same for each trial. Next, we shall look at various theoretical examples of geometric distribution. One example is in the world of business. A business owner may want to know the length of a time a customer will wait for some type of service. An employer who is interviewing potential candidates for a vacant position and wants to know how many interviews he or she has to conduct until the perfect candidate for the job is found. A police detective might want to know the probability of getting a lead in a crime case after 12 people are questioned. The mean and variance, skewness and kurtosis of the distribution are given as follows. Mu is equal to 1 by p, sigma square is equal to 1 minus p upon p square. Gamma 1 is equal to 2 minus p under root 1 minus p. Gamma 2 is equal to p square minus 6p plus 6 upon 1 minus p. Also, px is normalized since sigma x varying from 0 to infinity of px is equal to sigma x varying from 1 to infinity q to the power x minus 1 into p is equal to p multiplied by sigma x varying from 1 to infinity of q to the power x minus 1. This is equal to p upon 1 minus q, since 1 plus q square plus so on is equal to 1 upon 1 minus q, which is equal to p upon p, since 1 minus q is equal to p, and finally this is equal to 1. Let us understand it with the help of an example. In tossing of a fair die, what is the probability that on the fifth throw a face of 2 will come? Let A be the event that 2 occurs. Then probability of A is equal to 1 by 6 and probability of A complement is equal to 5 by 6. By applying 6.6, we get G of 5, 1 by 6 is equal to 1 by 6 into 5 by 6 to the power 5 minus 1, which is further equal to 1 by 6 into 5 by 6 to the power 4. Let us look at another example. A representative from a toothpaste company randomly selects people from Delhi city until he finds a person who is currently using any variety of the company's product. Let P, the probability that he succeeds in finding such a person, be equal to 0.7, and let X denote the number of people he selects until he finds his first success. What is the probability that the company's representative must select 3 people before he finds one who is currently using its product? To find the desired probability, we need to find the probability of x equal to 3, which can be determined by directly using the probability mass function of a geometric random variable with p is equal to 0.7, 1 minus p is equal to 0.3 and x is equal to 6. Probability of x equal to 3 is equal to 0.3 square multiplied by 0.7, which is equal to 0.063, which implies there is about a 6% chance that a company's representative would have to select 3 people before he finds one who is using any variety of its company's product. Further, we shall understand the meaning of hypergeometric distribution. Hypergeometric distribution is a discrete probability distribution which contains a relatively large proportion of the population in which a sample is selected without replacement from a known finite population, such that the probability of a success is measurably altered from one selection to the next. In other words, it describes the probability of x successes in n draws without replacement from a finite population of size n containing r successes. This in contrast to the binomial distribution, which describes the probability of x successes in n draws with replacement. The probability function for the hypergeometric distribution is p of x is equal to rcx multiplied by n minus r c n minus x upon ncn for x varying from 0, 1, 2 up to n, or r if r is less than equal to n, where n is the population size, r is the number in the population identified as a success, n is the sample size, small x is the number in the sample identified as a success. Also, in hypergeometric distribution, x cannot exceed r and n minus x cannot exceed capital N minus r. This distribution has three parameters, capital N, small n, and r. Next, we shall look at the theoretical examples of hypergeometric distribution. Choosing a committee of 7 from the legislature consisting of 52 Democrats and 48 Republicans. Number 2, you have a bag of 14 marbles in which there are 6 red and 8 green marbles. You randomly select 2 marbles without replacement and count the number green marbles you have selected. Number 3, choosing a team of 11 from a group of 16 boys and 13 girls. Slide 47. The mean and the variance of the distribution are given as follows. Mu is equal to nr upon capital N. Sigma square is equal to nr upon capital N minus r upon capital N minus small n upon capital N minus 1. The mean and the variance of the distribution are given as follows. Mu is equal to nr upon capital N. Sigma square is equal to nr upon capital N minus r upon capital N minus small n upon capital N minus 1. Let us understand it with the help of an example. In a class of 10 students, 4 of the students have failed. What is the probability of selecting a sample of 3 in which there are 2 failed? Also calculate the mean and variance. Given capital N is equal to 10, R is equal to 4, small n is equal to 3, x is equal to 2. We can solve it by applying 6.7. Probability of x equal to 2 is equal to 4c2 multiplied by 10 minus 4c 3 minus 2 upon 10c3, which is equal to 6 multiplied by 6 upon 120, which is equal to 0.30. Hence, there is a 30% probability of selecting 3 students, 2 of which have failed. The mean and variance is given as mean is equal to nr upon capital N, which is equal to 3 into 4 upon 10 equal to 6 upon 5. Variance is equal to nr upon capital N minus r upon capital N minus small n upon n minus 1, which is equal to 3 into 4 upon 10, 10 minus 4 upon 10, 10 minus 3 upon 10 minus 1, which is equal to 6 by 5 into 6 by 10 into 7 by 9, which is equal to 14 upon 25. Let us now summarize what we have learned in this module. The Poisson distribution applies when the events are countable, occurrences are independent, average frequency of occurrence for the time period is given. As per binomial theorem, P of x is equal to x, which is equal to f of x, is given by n Cx p to the power x q to the power n minus x, where p is equal to the probability of success, q is equal to 1 minus p, the probability of failure, where out of n events x are considered to be success. When p is small, the Poisson distribution can simulate the binomial distribution. For binomial distribution, Ex is equal to np, variance x is equal to npq, and standard deviation x is equal to square root of npq. Conditions under which binomial theorem is applied are: finite number of trials, trials are independent, only 2 possible outcomes, that is a success or a failure, the probability of success p remains constant from trial to trial. The Poisson distribution is not symmetrical. It is skewed towards the infinity end. The mean of any Poisson distribution is equal to its variance.